Sorry, just realized I was muted. Let me do that again. Thanks, Cody. Okay, so today's talk is by Manuel from LambdaClass, and I think it's one of the first forays of LambdaClass into Lean and form verification. So Manuel is going to talk to us about verified optimizations for zero-knowledge systems, and I'll let Manuel take it from here and put a link to the blog post about this work in the chat. Cheers.
Hi, everybody. Thank you for having us. My name is Manuel. I work at LambdaClass, and we've been doing some very enriching research with Lean, and we're very happy to introduce you to some of the ideas that we have been thinking about. At this time, we're going to talk about AMO-Lean, which is a framework for optimization within Lean. Okay, so we're going to talk about what the objects are and how we implement those objects in code, and some of the challenges we have faced, and our concept of optimization applied to cryptographic primitives. So this is going to be not a very long talk, and hope it's not going to be very boring, but we're going to discuss the idea. So what is AMO-Lean? So we're having automated math optimization. And the history of optimization is very long. Many discoveries throughout history made possible for people to do things in a better way. When you come from a math background, the notion of derivative is the central notion in optimization. Calculus was the vehicle for those ideas that were already implemented by trial and error to become somewhat together in a systematic framework. What we're going to discuss now is that it's a different idea and a different approach to optimization, and it has to do with graphs, okay? And the fact that we're doing this in Lean is that because you can already do optimizations by hand or systematically, but we need to have a certain proof that the optimized object still expresses the same thing as the unoptimized one, the one that you had intentions with in the first place. So that's the reason that we're looking into this thing. So to start the talk, we're going to talk about e-graphs. And to talk about e-graphs, we need to tell a little bit about term algebras. And it's not going to be very long, but it's more mathy than anything else. So we need functions. Those live in a signature that we call sigma, and it's a collection of functions. Each function has its arity that more or less says how many inputs does that function take. Functions with arity 0 are constants. So we have a term algebra, which is the smallest set containing all the constants. And whenever we have a function with n inputs and we feed n terms, then we have a new term in the algebra. Okay, for our purposes, we have a signature for FP, and that contains all the usual constructs that you learn in elementary school, say. Okay. The key question is, when should two terms be considered equal? Do you hear me? Is it going okay?
Yep.
Okay. Right.
Yes.
So what do we do with the term algebra? So we need to have an equivalence relation that will identify things that are equivalent, but also we need a congruence condition. This means that the equivalence relation needs to be stable under the application of functions that are in the signature. So this is kind of a closure condition that it's going to be very important for us. Okay, so whenever we have n couples of equivalent terms, whenever we apply a function to them, the results are also equivalent. This is for people from a math background, this is not strange, because we, in many fields, like in algebra, we demand equivalence conditions to have some extra closure properties. In this case, we're going to have this one. And the example is clear. Okay, so if we deem a times 2 and a plus a to be equivalent, then any function that we apply to those terms need also be to be equivalent. And here comes the construction that is central to us, an E-graph. An E-graph, it's an equality, an equivalence graph. And it is a representation of the quotient algebra. And it has two parts, the two sets, and a function of membership. So on the one hand, we have the nodes that are represented as functions from the signature evaluated at classes terms, and we have the equivalence classes that are the natural concept. This membership function assigns to each node its E-class. Okay, so in this sense, we have a bipartite graph. And the congruence invariant makes sure that whenever we apply F, we have equivalent terms. This way of looking at E-graphs already shows that since we can apply functions to terms and the result is also a term, what happens when we apply a function again to the previous term? This begins this nested soup of terms and is one of the main concerns of implementations of E-graphs, but also the power of its expressivity, so to say. So just for a short example, suppose that we start with 3 nodes, a times 2, a plus a, and 2 times a. Those nodes, they all belong to the class of 2a. That's the class C1. But also we have the class of A and the class of 2. So there are some arrows that one can draw between E nodes and E classes, and those arrows can differ in their meaning, what they say. We can point to the children classes, which are the classes of the arguments, and we can point to the proper class of what the node is actually doing. In this case, the class C1. And this implies that within classes, we have a hierarchy. C1 is considered to be the parent of C2 and C3, okay? So this is the kind of object that we're dealing with. The way we represent nested terms is from the bottom up. We resolve the children first, and then resolve the intermediate expressions, and then get the full term. This is, mathematically, this is not complicated to understand, because in math, you just state what you want to say. But when we cross to the implementation side, this is going to be a little bit sketchy, okay? So if 2 terms share a common subterm, that subterm maps to the same equivalent class. This structural sharing thing is what allows the expressivity of the E-graph. So from an algebra perspective, we're dealing with a quotient algebra that has this special congruence property. We're not going to go any further with the math, but this section introduces like the basic object, and we're going to be now heading into what are we going to do with this thing. So here comes the equality saturation algorithm. This is known for a number of years now. This paradigm is, if I'm correct, dates from maybe 2009, and it's been getting more traction in the machine learning community slowly, and we're going to exploit that here. So before going into saturation, we need to talk about some operations that take place within this paradigm. Substitution, the first thing. You replace terms with other terms. That's something when we formally manipulate polynomials, or maybe if you have experience in algebra, you do that all the time. That's how we first approach rewrite rules as students. Okay, we can replace things inside other things, and it's basically composition that acts for us at a syntactic level. On the other hand, we have valuations that operate more in a kind of semantic level, because valuations are the way we have of assigning meaning to things. So for us, a value that a function attains stands for its meaning. So semantics is the bridge between the syntax and the values. So for each function in the signature, we can provide a function and actually work in an existing function that takes values in a set A, in a domain A. E-matching for us, it's doing substitutions, and soundness is stated over valuations. So what are rewrite rules? A rewrite rule is a subset of the repetition product of the term algebra with itself. In terms of elementary algebra, a rewrite rule is a relation that satisfies this additional property. So a rule is sound with respect to semantics if for every substitution instantiating the pattern and every valuation, we get equality. Okay, examples are like the ones that we have in mind. I mean, x times 2 and x plus x, they both form a rewrite rule. And why is that? Because doubling is adding to itself. Same with commutativity or having an additive neutral element. Okay, so soundness for us means that if we apply the rewrite rule, we never change the semantic value. This implies that we can have an e-graph, consider one of its nodes, and start scanning for all possible substitutions. And we are going to keep the ones that are semantically equivalent. This means that the classes will grow. Okay, it's not going to delete terms. And here comes the problem we want to address. Okay, so whenever you have an optimizer, maybe in the guise of a compiler, many times the compiler reads a line and reorders what it reads. Parsing gets acted on. And sometimes that rewriting destroys the original term. And in many cases, the rewriting can be done in different ways. We are going to address this problem because destruction of the terms for us, it's kind of a complicated thing. Okay, we want to take into account all possible rewritings of a term without destroying them. And the thing is that depending on the way you rewrite, the cost of processing that expression will change. Mainly because we want to apply this to computers, and computers have hardware, and not every operation costs the same. So it is vital for us to be able to rewrite in an optimal way. So equality saturation is a paradigm in which we consider all possible rewritings of an expression. So the saturation algorithm, what says is you take an input term T0, deconstruct an e-graph, you add that term, and you start to saturate. By substitutions, you start saturating the class. And you're going to keep all the rewritings that are sound, that are compatible with the evaluations. Once you do that, you have the problem of extraction. Okay, so I have this bag full of semantically equivalent expressions. How do I pick the cheapest one? Okay, and once you resolve that problem, you have an optimal output that is semantically equivalent to the input T0 or T0. That's the basic idea of what we're doing here. Now, how do we do this on a computer? This is not an easy task, and we need to teach the computer to do these things that I described in math and described in colloquial language. So, as of now, the quotient algebra is a mathematical object, has no life outside our intellect. So in order to implement this in a computer, we need to construct functions that they operate at different levels, add, merge, find, and rebuild. They all have a place in the construction of the graph, and they all take place in the saturation part of the equality saturation algorithm. We need those things. We need those functions. And these implementations need to be done kind of carefully, because the classes can grow. I mean, they can really grow. And whenever we merge classes by identifying semantically equivalent expressions, the reference to those terms can be broken. And so we need to rebuild them carefully. So these operations, add, merge, find, and rebuild, use typical structures in computer science, a union find and hash cons. Union find is a classical data structure that helps to maintain clean disjoint sets. And hash cons, for us, help us to guarantee deduplication. Okay, what they do is they keep track of where the classes are. So an example, so maybe we have A times 2 and A plus A. Before you had 3 classes, C1, C2, and C3. And we know that if we add C3 twice, we get A plus A. Class of A plus the class of A points to C1. And when we do multiplication of C3 and 2, we get C2. So we have 2 pointers, one to C1, the other one to C2. After we merge, see, when we actually decide that A times 2 and A plus A are equivalent, now they melted together in a single class, but the pointer that looks at the product of C3 and 2 is outdated. So we have to rebuild it by chasing all the reference with the hash function. This merge and rebuild functions are necessary for the construction of the E-graph, and also they're necessary at the stage of saturation. Okay. What's going on behind all this is that this consistent valuation property, we're going to make sure that all the elements in an E-class valuate to the same thing. They have the same semantic value. And this is an invariant constant that is going to be present throughout all the algorithm, all the protocol of equality saturation. This needs to be preserved, okay? It's present at construction, where we build the E-graph, and it's also present during the saturation process. So the loop looks like this. We start with a term to 0, we add it to the graph, start to saturate after matching by applying rules, and then rebuild the whole thing. Once we get a nice and fat E-class, we proceed to extract. And when we are done with that phase, we have the optimal rewriting of the original term T0. This saturation loop happens until we reach a fixed point or until we run out of fuel. What does this mean? Since this can grow very, very fast, we want to ensure termination of this loop. And this is a practical issue. This doesn't happen in math. Okay, this is a really practical thing. So fuel is to be implemented wisely. Maybe if you have very little fuel, you saturate too quickly, you have too much fuel, you run out of memory. But the thing is that for the applications that we have in mind, fuel is not a problem yet. Okay, is it clear for everybody up to now?
Yep. I think if anyone has questions, I think they'll jump in, but it seems very good so far.
I'm not looking at the chat, I'm looking at the slides, so feel free to interrupt me. Okay.
Yeah, I can look at the chat.
So we have proved a theorem that says that if all the rewrite rules are sound with respect to the semantics, then for any term that we have in the input, we can extract an optimum term, an optimum rewrite. As of now, we can guarantee that the output is sound, maybe suboptimal in case we run out of fuel, but it's always sound. And we don't need any hypothesis for this engine. We have no custom axioms, and it's verified end-to-end by Lean 4. Okay, this idea, this engine, we've called OptiSat. It's a standalone engine that does this specific thing. Okay, we have a theorem for that set of code, and AMO-Lean will instantiate OptiSat for our crypto environment. So this is already proved, and we're going to find many, many, many more uses to this engine. So the challenges that we're facing in the implementation of this idea. First of all, how to build an e-graph. There are precedents of this technique. Maybe people that come from Rust know already some of them. And the reference for equality saturation is called egg. It's a very nice sounding name. And the way egg works is that it uses pointers. They use that because they can, and it's a neat way of keeping track of things. But for us, this is not so easy, because pointers and memory usage can be controversial, or at least for me. So we had a solution, because we're not going to use pointers, we're going to use flat tables. And nodes are now flat data. They have an operator and a list of children. Classes are integer keys into a hash map. And union find for us is a flat array with counts of references. This architecture for us avoids cycles in the heap and help us keep things as simple as possible. Of course, there can be other strategies for dealing with the pointing, but for us, our first idea was this one. It's practical, short, and easy. Now, second challenge, or challenge number one, the eGraph explosion. Saturation can grow. I mean, just commutativity alone generates infinite variance if you apply it naively. So we have some guardrails to the explosion. First of all, we have fuel-bounded iteration that appear in different levels. First one, we run through all the possible substitutions. That's called the image fuel. Then we have the saturation fuel. It's the number of rule applications that we have. And we have the rebuild fuel, how we reconstruct the classes. Of course, we always have sound results, but we can sometimes obtain suboptimal results. Then we have this idea of rule classification, because some rules will increase the cost of the resultant expression, some others will reduce it, and at this point we're choosing reducing rules only for safety, just not to have the computer explode. And then we also have this idea of canonical ordering, not to force it as maybe as a rule, but it's a deterministic structural hashing. Okay, we have a canonical order for the operands. We are sacrificing completeness as well, but we guarantee termination in those cases. And now comes a big challenge that it's called the optimal extraction. This problem is hard. It was shown in 2011 that this is simply hard because we can have sharing, like we can have many hours going from nodes to many places. So the way we're dealing with this difficulty is by considering three different ways of extraction. We have a greedy extraction that's locally optimal. Greedy extraction has a long history. It works sometimes for us, some other times it doesn't work, but we considered it. We also have an integral linear programming perspective to this, and this is globally optimal. But we're using an external solver, and the results of the solver we verified. And then we have a dynamic programming approach that uses a characterization of e-graphs that it's very, very interesting because we're going to be able to rephrase or reconstruct e-graphs as trees. So greedy extraction, that's the simplest. For each class, you compute the cost of every node and start chasing up the graph. We pick the minimum cost, and that's our result. Works when the graph is like a tree. Each child class has only one parent, so local choices are also globally optimal. There are no coupling between decisions of rewritings. This fails exactly when you have multiple parents. We can pick like a local optimum and lose the global picture. The loss can be up to 40% versus the true optimum. This idea and this assertion came from a paper from machine learning theory. Then we have an idea of rewriting the extraction process as an integer linear program problem. So we have to minimize a big sum where now we have a variable xn that tells us when the node n is actually active or not. So these sort of problems have a long, long history in mathematics. They've been studied thoroughly for, I don't know, maybe 5 or 6 decades now, or maybe more. And the thing is that we do not solve this problem. We can state it, and somebody else solves that, and we check the solution. This is some sort of Oracle checker pattern that we have. Whenever we get a result, we check if that is consistent. We have a number of criteria to check if that is actually sound or not. This is another approach that we tried, but one of the really important things is that we are not going to be stuck with ILP. So we can achieve optimality within Lean without an external solver. And we need to have this notion of bounded tree width. I don't know how many of you come from graph theory. I am kind of a newbie to graph theory. I might have a different background, but it's a very nice idea. So whenever you have a graph, if you draw bags covering edges, you can join those bags whenever they share a vertex. There are many ways of rewriting this tree decomposition, and to compute the tree width, you take the minimum of all possible rewritings and then subtract 1. This tree width measures how tree-like a graph is. And the good thing is that for our applications, this is feasible to do. A second example, I'm sorry. A cycle with a chord. We have different bags that we can write right on top of this graph. Different configurations lead to different edges between these bags. And the thing is that for our purposes, the tree width is going to be very low. These are tree width 2 things. We're going to be dealing with e-graphs that show tree width that's below 10. That's a very nice thing for us. And why do we bother to talk about tree width? It's because in 2024, it was shown that e-graphs can be cast as interaction graphs. They go through this idea of converting first the e-graph to a circuit that's monotone, has only AND or OR gates. And those circuits can be translated into an interaction graph. So once you have this interaction graph, you measure the tree width, and if it's small enough, you can apply dynamic programming to that thing. And then you backtrack all the way to the e-graph to read the expression that you get out of the algorithm. So the compute time for this is polynomial in n, and it's only exponential in the tree width. So the tree decomposition for us will work. So in summary, the full chain from e-graph to optimal extraction will go pretty much like this. Take the e-graph, translate it into a circuit, translate it into an interaction graph, and then translate that into a tree decomposition. But since there are many tree decompositions, you need to find a canonical form. That's what in the literature is called a nice tree decomposition. We're not going to dive into that, but that's how DP actually works. So the contribution of Sun is very important because it allows a very nice paradigm of extraction to be applied to e-graphs. This is very good news for us. Once we described like the challenges and what the objects are, let's talk about AMO-Lean, which is what we've been working on this past few months. So what are the components of AMO-Lean, of this optimizer for arithmetic expressions? So we have an abstract e-graph that provides the framework and the proofs. That's called OptiSet. It's generic. We're going to instantiate this motor in very different environments. We have written algebraic specifications of maybe entities or other algebraic constructs like matrix products, Kronecker products, triddles, and things that are basically definitions. And we also are going to feed AMO-Lean with fine fields and their structure and verify reduction theorems. The real moving part here is this orange or kind of a yellowish square. This is what's actually moving in our construction. We're going to feed the structure, the definitions, and the primes, okay? This is going to perform the equality saturation algorithm, or it's going to output a rewriting of terms in C or Rust, okay? So type classes for us are the mechanism to connect the original motor with AMO-Lean. We're instantiating AMO-Lean at arithmetic level right now. All the theorems are already proved, so proofs come for free. What we have formalized and we have constructed is this kind of library of things that we're interested in. Finite fields, we have Mersenne, Baby Bear, Goldilocks, Koala Bear. We're planning on adding more. We have definitions and proofs of theorems that we know correct. Hashes, polynomial evaluations, verifying soundness, like all those things. And the good thing is that we are going to feed all this to the motor. we're going to make explicit the first part of the talk by saying what are the elements of sigma, what are the functions that we're going to be applying terms to obtain new terms. So we have algebraic constructors, bitwise, and Kronecker constructors. They are functions that we're going to consider in our signature. These are relevant for us. We can add more. At this point, this is really up to us. I mean, whenever we find a new constructor that's valuable, we can add it to this bag. And now the rewrite rules. Rewrite rules are the responsibles for the building of the graph. Each rule that we have has a sound proof, and they apply and preserve semantic equivalence. Shifts, identities with and, or, and XOR. We have fold operators. We have reduce operators, butterflies, all the things that we want to mix together really hard and see what comes out. And here comes a very nice and important part, is the cost function. It dictates the way we extract the optimal choice. At this point, this is largely customizable. We can, it's up to us how we design this cost function. At this point, we have this proof of concept that it's very basic because it only thinks about cycles at the ALU. This is a very basic design still, but it leaves a lot of room for improvement. And this is what's going to summarize what we have been doing, like humans. All the optimizations that we know have been the result of years and years of trial and error, of improvements at the hardware front, improvements at the software front, new ideas coming from math, coming from engineering. This is a largely human enterprise to optimize. At this stage, our cost function is basic, but it's really plug and play. We can teach the cost function to be more expressive, to have more granularity, to take into account many, many more things. But at this point, with this very basic design, we already have very promising results. Okay, so at this point, we're only looking at cycles of the processor. So every primitive that we're going to consider takes field operations and also needs to implement the reduce operation. Improvements in that part alone multiply across the whole primitive. Just for you to have an idea, when you're talking about entities, if we have 3 per butterfly, when you have production size, you're talking about 30 million cycles. That's 8.5 milliseconds that you can save. So the relevance of how you reduce cannot be overstated. At this point, there are a few strategies for reduction that are very well known in the literature, but maybe we can find more. Okay, so this is very important for the purpose of AMO-Lean. So practical implications, say you shave 1 cycle, at scale, it says a lot. Say 1 cycle per reduce at 3.5 gigahertz saves 19 milliseconds per entity. If you run 100 entities per proof, that's 1.9 seconds saved per proof. And if you run 1,000 proofs a day, that's 30 minutes worth of compute. Try to picture that if you save 2 or 3. And we're only talking about saving cycles. We're not talking about more sophisticated heuristics that we humans know. The eGraph doesn't know about implementation. The eGraph just knows about rewrite rules. But if we supply a rich enough cost function, this can work. So our results at this point are really promising. This is still a proof of concept because all the scaffolding has been done, all the wiring has been done, but we still need to teach this, what it's dealing with. And we have strong reasons to believe that this can yield very, very promising results. And one of the things that, for me at least, is comforting is that we can produce verified code that's faster than unverified alternatives. Usually, people portray verified languages or verified code as something slow or something inconvenient. I think that can flip. And we have only explored a really tiny fraction of the optimization space so far, but we have already found very promising things. So trust and positioning, how we guarantee correctness. This is all the work that has been done in this area came from your feedback at the Telegram channel. And it was a very, very fruitful exchange. So what about the code gen? The expression that the eGraph produces goes then through 3 stages. We built a kind of a standalone intermediate representation processor for the backend called TrustLean to be flexible enough to be able to take in different representations from an eGraph and parse them in a verified way. So the first pipe is going from the eGraph to an expression tree. So the optimized code that an eGraph produces, it's then translated into something that has to do with low-level expressions, okay? We have a theorem that proves that every expression evaluates correctly after translation, covering all the constructors that we considered. Okay, so we have a theorem that's called lower mixed EPS to LLE evaluates. Not a very nice name. Then we have the second pipe from the expression tree to formal C. We have this micro C version that is a subset of C99 that deals explicitly with numbers. We are not going to target general C code. We're just only interested in the code that eGraph from AMO-Lean produces. So we're good with a subset of C. Okay, this is where you catch bugs like truncation and how numbers fit into U32s or E64 chunks. So we have that theorem that proves that correct, STMT to micro C correct. And the last stage is formal C to C source text. Okay, we have a round trip theorem that proves that the parsing from the emitted string produces the same thing as our micro C tree. Okay, this was done after the interaction with you guys at the Telegram. So a few words about TrustLean. This is modular. Provides a core intermediate representation, works with micro C. Has 2 backends. We're going to encase this in the future with more backends. I mean, we want to use this more, and it's modular because we want it to be modular. And it interacts with AMO-Lean just to do its work. Okay, and it's going to be available for other projects as well, and we like this idea as well. So how AMO-Lean compares to other equality saturation engines that are already out there? Well, the reference for everybody is egg. That's done in Rust. It's very fast, but it has no verification. And that's the thing that we want to have. Okay. It's all Rust code, and it only uses heuristics and greedy extraction. It's generic enough to be applied to many places, but we're interested in verification. There's another effort called Lean Egg. It has a couple of years now, but the author, Russell, has been very active in that field. And the main difference with AMO-Lean is that the way it verifies things, the actual saturation motor is outside Lean Ag. And in our case, this is fully within Lean, okay? So Lean actually reconstructs a proof in Lean that's been handed by another motor. We don't have that. We have a fully Lean thing going on. So future directions, what we already have, we have a verified eGraph motor. We have bitwise constructors and rules that are the ones that are working with us. We already modeled Bowers entity. Our selection model is aware of the primitive, and we have very promising results even in this setting. There are many more things. We have current packing, lazy reduction. We have 4 targets. We can add more if needed. Like at this point, many parts of this project are, I don't know how to pronounce it, but you can customize many things. Like it's really plug and play for the most part. And AMO-Lean has clear objectives ahead. One of them is providing a proof for the optimization. It can be checked outside Lean. We're thinking of maybe exploring new primes. And most importantly, adding expressivity to the eGraph. That's a central objective for us. It's very close. We already have advanced work in all those 3 things. Then for the ZK ecosystem, we already have a very advanced proof of concept to verifiably optimize constraint circuits. We have a prototype. We need to finish some things, but we are very advanced in that, and also in security analysis using Lean. Really, the applications of this equality saturation engine are really flexible, and we're going to be studying the possibility of studying security standards with this kind of technique. Also, there are many other applications that go outside crypto. We can have database theory explored, also AI and tensor analysis, and also numerical analysis is a big one for us. Now, we're very optimistic, and
Manu,
we're very we have.
and I add
Yeah.
that we're also Diego Kingston, that is in the call, that is leading the research team in Lambda. He's a chemical engineer. We have quite a few ideas on how to apply these on traditional more sciences, so not related with cryptography or computer science. We're still working on it, but we're pretty confident that in places where normally you need to do a lot of physical work, but there are symmetries or different properties that we can write on code on research by minimizing or like looking for the function we want. We can find interesting things. We didn't yet. We only did it in cryptography, but we're pretty confident this will work in other places.
Oh yeah, I mean the framework is really promising, and the fact that we are able to produce formal proofs for this is very promising. So the key takeaways for us is that the eGraph paradigm works. As far as we know, OptiSat, the generic engine, is the first one out there doing this fully within Lean, and verified code can work very well. And we're going to have many more news, and some numbers are going to be coming soon. And we're conservative, but at the same time, we're very optimistic on this idea. Okay, and thank you very much for having us and for listening. It's 10 minutes to 2. I'm sorry if it's been too long.
Manu,
Here is references. Yeah.
I asked Manu not to show some of the numbers we already found because we want to double check them on. We're going to do quite some engineering work, but we're pretty confident they're correct. Can you share some of the numbers we already got?
They are out of the slides, but we need to be thinking around maybe 20%. They're very promising. Maybe we can share them afterwards, but right now I don't think I have them in the slides.
If not, you can share them on Telegram later.
Okay.
And I can always add them to the YouTube description of this video or something like this if you have anything you want to share.
It's okay for me.
Okay, then I think, well, we have some time for questions. I think I have at least 2. I know Baz already has a few in the chat, so I don't know if anyone wants to unmute and ask some questions. And we can obviously go over the hour as long as Manu has time. I see Natalia is raising her hand.
I have time. I need to figure out how to do the sharing with the screen because I'm sharing the full screen. Just go ahead with the questions. I'll just answer.
Thank you. Yeah, I have a question. Thank you for the presentation. My question is, for a team already running Plonky 3 in production, what does the migration path actually look like? Do they rewrite specs and lean first, or how it would look like? Thank you.
Oh, thank you for the question. This is still like a prototype, and we're producing verified code already. So it's up to the teams to adopt this code or not. It's going to be, I guess, minimally invasive. Like, it's not going to be like a great deal, but you know, Plonky 3 has a long history. It's a long collaborating work. Many people have worked at that, and they are also considering many things that we're not. So the comparison, and maybe it's not that easy. Let me see if I can find the right slide. This is what we're working at right now. We're not considering memory optimizations, access to memory. We're not even considering all the things that Plonky 3 already has working on. So we're not there yet, but maybe it's going to be not that complicated. I don't know if I answered your question, but within some time, that will be more clear for everybody.
Thank you. Makes sense.
I would add that the core roadmap would be that if we find something interesting, like, for example, optimizing entity or the fields, the first thing we're going to do, and we're doing, is checking it out in our LambdaWorks implementation. Then we're going to speak with Plonky 3 team to see if they like it. Since it's proven, it can be formally verified, but also tested out. If they like it, what we're going to try is to make sure that the improvements are merged upstream. So in theory, if it's something that is inside Plonky 3 and the results are good, there shouldn't be a relevant change in for the users of Plonky 3. Right, Diego? So this is more for research. As soon as we find something, we're going to try to obviously publish it. We already found a few things, and we're going to push everywhere to adopt it. So the idea is that the user doesn't even see. It's just a PR to the original to all the repos that we can.
Yeah.
Baz, yeah, go ahead, Baz.
Yeah, very, very cool work. I was wondering whether you looked at CraneLift, which seems to be has some similar ideas. So it's a Rust compiler, and they explicitly want to do formal verification. So your work seems very relevant there. And I had some other questions about Cryptop, which does automatic optimizations of cryptographic code, and then there's the Bedrock C language. I was wondering how it compares to your micro C.
Okay.
Manu, can I, if you want, go ahead, but I think
Go ahead.
any
Okay,
questions,
yeah, go ahead.
I think, for example, crane lift, I don't know if how much Manu knows about it. So the issue of all these things is that you need somebody that comes from mathematics like Manu. Then we have inside Lambda, we have people that work on the compiler of Rust, on crane lift. For example, I know way more about that than Manu. And I think crane lift is trying to do things like this, but they will, like, this is more for the research on being able to find something. Crane lift in general, what's trying to do is make more efficient the already compilation of Rust. So yes, it's similar, but what we're trying to do here is like it's actually more similar to what you mentioned, Cryptop, in terms of like finding something and then pushing it upstream. Currently, if it's trying to make sure that any change they do on optimization is correct, at least from what I am aware in Rust. So yeah, it's similar, but we're doing like, we're more in the not automatic, like, yes, it's automatically generating formal, faster code. That for us, it's more like to find new things on crane lift, to make sure that the things that are being produced are correct. On the second difference is like, I'm not an expert in Cryptop. I have seen it before, but from what I see, based on what I know on Cryptop, is that the type of optimizations we can do are way better thanks to the graph on the all the space we can analyze. So this is in a more like higher level type of search space. On that's why we're finding amazing things. Like Cryptop is trying to generate good code, formally verify that the code is correct on refitting it. So from my point of view, this is a bigger finding on where, if we're correct, maybe we're not, but we're gonna find many interesting things, and that's what we're already doing in ZK. We're gonna try to extend it everywhere. So I don't know, Manu, if that added up something, but I wanted to make sure that the crane lift part is, from my point of view, a little bit different, but yeah, they're connected.
But I mean, could you re-implement crane lift on top of your framework? For example,
Yes,
what are the limitations?
I have a better idea than that. We're implementing a better programming language than Rust, but that's another discussion. Like, we're creating a formally verified Rust. We can discuss it afterwards if you're interested. But we worked on the core of crane lift, on Mir, on all those things for years. From my point of view, it's fully fucked up. Everybody's going to use it, but there's better ways of doing it. I'm an engineer, so I don't want to do it for a paper. We believe there's ways of doing something like what you're saying. Like, it's a 10x better. Like, if you're interested, we can discuss it another day. It's called Concrete. We're working on it with many people in Lambda.
Yeah, very interesting.
Yeah, I'm just going to add that I have a math background. Like, I'm a differential geometer, so the really technical engineering questions, I'm not going to be able to answer like fully, but the ones I can, and otherwise I'll just leave you to Fede.
Okay, so I have a couple questions, but I'll start one which is straight from the talk itself, which is, early on you mentioned obviously you were sacrificing some completeness, for the sake of having things actually run. Do you have a kind of concrete sense of how far away you are from completeness, or any kind of measure of that, or is it still, maybe there's some gains to be made from letting things run a bit more?
Good question. How far off we are from optimal, I don't know. We know that our output term is sound. I really don't know how far off from optimal we are. But maybe we can, that's a good idea. Maybe we can have a sense of how far off from optimal we are. This strategy for fuel, where is it? This strategy for fuel has been working very, very well. Just for you to have an idea, the first versions of this code exploded really quickly. After maybe started with 2 classes and 5 rewrite rules, we were having 100,000 classes very, very quickly. So it was really a need for us to impose these guardrails. What works really nice is the director rule classification scheme and the canonical ordering. those are things that are kind of natural to ask for. The fuel bounded iteration is the one that is actually something we impose because we want the program to run. Maybe we can have a different approach that doesn't need fuel. Maybe we can further on to maybe guarantee termination with a different kind of architecture. But as of now, we need fuel. It's a good point to make and a good point to think about. Thank you.
Yeah, so a kind of lead up, well, to lead up to the second question I had, which is that in some other kind of component frameworks, and think of MLIR specifically, you will see in maybe things like HARE, which is this IR for homework encryption, they have a lot of benefits from having high-level IRs that preserve more mathematical structure and finding optimizations at that level before going down to lower level IRs and finding other optimizations there. And I guess there's a question which is maybe you've explored or maybe you haven't explored, but are planning to do so, kind of looking at different IRs and rewrites at different levels, and maybe getting better completeness by having different IRs with fewer operations and fewer passes, which means that things might not blow up as much, and then just doing this iteratively over different lowerings.
We have already been working on that, and it's not in the presentation because we're still working on it, but it's part of the enriching the expressivity of this thing. At this point, what's actually grinding, it's this orange block. It's the low-level arithmetic irref. This is what's running, but we have many ideas in order to move the optimization to the algorithmic side, in the sense that maybe instead of ordering the elements of the entity in this way, we can order them in a different way, and we can get some extra edge to the optimization. That's going to happen. It's already going on for AMO-Lean, and we're very positive about that.
Nice. Yeah, that's very exciting.
One question about what you said, Alex, because we're already exploring that area, but we do work quite a bit with MLIR. We implemented Cairo native, like the compiler of Cairo in MLIR, but I'm not aware of the thing you mentioned. Can you repeat it? Like there's which is the IR, the intermediate, like which one? You said there's one that you said something about.
Yes. I'll put a link in the chat. So there's this HARE or HEIR, kind of different people pronounce it differently. But it's a set of dialects for homework encryption that is used by Google, and it's fairly applicable actually. There's quite a few dialects there, like obviously for modular arithmetic, that carry over, to the ZK case. And in some cases, we have an RFC coming to actually upstream the mod arith dialect to upstream MLIR. That's another topic. But there's also, they have some linear algebra dialects and things like this to do optimizations, obviously at a much higher level on mathematical structures that you don't find in lower level IRs, and that's been quite fruitful. I think with HARE now, if you want to I'm using that as an example because it's fairly mature and used in production. I think now that they're pushing towards having kind of 20 dialects, so that they are accumulating things, but every dialect is kind of simple in that there's maybe 3-4 operations, and so you might be able to obviously optimize with a greater degree of completeness on each dialect, and then obviously lower, rerun it again on another dialect. And we've been exploring trying to do similar things for ZK circuits, right, with LLZK and all of this. There'll be a couple of talks in April precisely about MLIR and MLIR verification and LLZK, which is MLIR for circuits, in April or May. So maybe we can rediscuss that at that time. But it seems like maybe a nice thing to look at, and so it's very exciting that you're looking at it as well.
Yeah.
And then another part of that is obviously with MLIR, as you'll know better than I do, is you obviously have kind of good support for GPU backends, which is also interesting.
Yeah, the last mile we're still working on. We want to be more expressive, And this only has future. Like there are many things to be done yet, but we're very happy it works. Like start, it's good.
Yeah, fantastic. And then I had one tiny little question as well, which you can choose to skip if it's basically not relevant. But you, at the very end, you mentioned obviously you had some work that was ongoing on precisely kind of IVC and improved carrying data. And I was curious if there was more you could say about this, but purely out of interest because it's something we're starting to work towards as well.
Well, maybe we can have not only lean code, but we can also have something that you can execute that assures you that the optimization is correct. We know it's correct within lean, but for the outside world, maybe we can have certificate that the optimization is correct. That's what I'm trying to say with proof carrying optimization.
Okay, yeah, that makes sense. Okay, yeah, fantastic. I don't know if anyone else has some other questions. Otherwise, because I think we're already above the hour and other people might have meetings. I'm conscious to not try to ask too many more questions. But if anyone has any last questions, then now's a good time. And otherwise, we can call it a day and keep discussing it on Telegram. Yeah, go ahead, Dimitris.
Yeah, sorry, I just have a very quick request to attach the slides to the maybe Telegram. I may have some questions on some pages of the slides, but I would like to ask them in some other time.
Okay, sure, no problem.
Thanks
Sure.
a lot.
Oh, thank you.
Okay, then yeah, I'll stop recording and we can call it for now. And yeah, if there's any more discussion or questions, then obviously Telegram is a good place to start this. Yes, thank you for the really nice talk. I think it's very exciting work, and it's very exciting to see LambdaClass get into Lean and all of this. And yeah, hopefully maybe we get a talk about concrete at some point. That would be quite interesting. On our side, we're exploring just using Lean in production, so it'll be possibly quite complementary to what we're looking at. So yeah, thanks everyone for coming. Thank you, Manuel, and looking forward to much more work in that direction. Cheers.
Thank you for having us. Goodbye, everybody.